And I would like to extend thanks to all the organizers of this workshop. Thanks for having me here. It's been a great pleasure to be here. All right, so my talk will be about cosmology. We've already had several talks about that, but I guess mine will be sort of more focused and specifically in the context of large-scale structure. So cosmology, as you know, is a very successful, very mature field that has experienced a lot of progress in the last 20 years or so. Now we have a very coherent, consistent picture of the universe. That it all started with inflation. That was the primordial accelerated expansion of the universe that happened before the Big Bang. And then inflation created the primordial fluctuations. And then after inflation, the universe was expanding and cooling down. At some point, these primordial fluctuations, the universe cooled down up to the point that the first atoms were created, and this gave us the very first image of these primordial fluctuations in the form of the CMB. And then later on, in the lower redshift universe, we also get to see galaxies, which provide us even more pictures of the primordial fluctuations. And in cosmology, we have the standard model, lambda CDM, that explains, in a sense, all these observables, all these pictures with very few external components. So some extra stuff that needed to explain it is inflation, cold dark matter, and the cosmological constant, at least. And this picture, even though it's very coherent and successful, it left many open questions, known unknowns. So we don't know what was inflation exactly. We don't know what is the nature of dark matter, neutrino masses, etc. And also we're hoping to see maybe some unknown unknowns, so surprises in the data that will totally change our perception of cosmology. Okay, so in terms of different components that I mentioned, dark matter, as you know, contributes to 26.8% of the total energy density of the universe at redshift 0, and there are many independent observational tests that suggest dark matter, such as the strong gravitational lensing and also the fluctuations of CMB and large-scale structure. And so we know dark matter gravitates just like usual matter. It just does not shine, and that's why it's very appealing to assume that dark matter is represented by some particles beyond the standard model, and there is a whole landscape of these different particles. And I should say that despite very significant progress in experimental constraints of dark matter particles, still, all this landscape is pretty much on the table. In terms of dark energy, it contributes to something like 68.3% of the total energy density of the universe. And recently, there's been some excitement related to the tantalizing hints of the time evolution of dark energy observed by the DESI collaboration. So this field has become very hot again. And from the theoretical point of view, dark energy could be a cosmological constant. This is the simplest explanation. So, there is this very nice train wreck in a Bolivian desert with the Einstein equations scribbled on it. Unfortunately, we don't have the cosmological constant, so I added them here. So cosmological constant is a very natural solution to it, and a lot of people believe that this is the explanation for dark energy. But given the recent DESI results, people again discuss other possibilities, such as having a scalar field that slowly rolls over its potential, some sort of quintessence models. All right, so we still don't know what it is. Roughly speaking, we need better measurements to figure this out. In terms of cosmic inflations, we already had many great talks about this. Basically, the idea of cosmic inflation is that you need to stretch the universe at the very beginning exponentially fast. And originally, inflation, as a mechanism, was proposed to solve some of the problems related to the initial conditions of the universe, specifically the correlation between different, let's say, patches of the sky that were never in causal contact with each other. So inflation explains this very nicely. But after the original proposal of inflation, there's been a lot of work regarding other physical scenarios that could happen during inflation that could be tested. And I feel like now inflation from a mechanism that was designed to explain some problems now has become a new tool to actually test particles and interactions at the highest possible energy scale. And thanks to the speakers that gave their talks beforehand, I don't need to explain what primordial non-Gaussianity is. But primordial non-Gaussianity is a absolutely wonderful phenomena that allows you to probe a variety of different new physics scenarios involving particles and interactions. at energy scales that could be as high as 10 to the 14 GeV. And let me just say that it's absolutely imperative to use the large-scale structure data to probe inflation, because CMB simply doesn't have enough information, doesn't have enough modes to make progress on measurements of primordial non-oceanity. And one of the goals of my talk is to convince you that we have all the tools necessary to, to achieve that, necessary to probe non-oceanity with large-scale structure. And we're living right now in the dawn of the precision large-scale structure science. So in cosmology, we have a very precise definition of what is information, which is the number of modes. And here in this plot, I'm showing you the number of modes as a function of year. And at the beginning of cosmology, galaxy surveys were the only source of information. And then, galaxy surveys provided some sort of learning curve that is sustainable and that can help you measure, in principle, more and more modes as you go. But at some point, we discovered the CMB, and the CMB offered us much steeper learning curve, and we have been exploiting, in the last 20 years, we have been exploiting this curve. But unfortunately, the amount of modes in the CMB is fundamentally limited by the fact that CMB is simply a plane, and that's why we cannot really go much further than that. And that's why we're hopping back onto the information curve, the learning curve suggested by large-scale structure, and the current ongoing surveys, such as DAISY and Euclid, they will already match the precision of Planck very soon, and future surveys, such as MegaMapper, will overcome CMB in terms of number of modes by orders of magnitude, and then, well, actually, this plot will be continued even further with, let's say, 21 centimeter observables, etc. And already in, on time scales of, let's say, 5 years or so, the precision with which we measure typical cosmological parameters will be an order of magnitude better. So here you can see, for example, what kind of error bar we expect from on the Hubble constant. So right now it's 1%. In the future, in 5 years or so, this will be 0.1%. So this obviously means very dramatic improvement of our measurement, and this opens up really, possibility for revolutionary discoveries. But however, the problem large-scale structure is that, unlike the CMB, large-scale structure distribution is nonlinear, is very sensitive to nonlinear effects. And if we take a look at the, let's say, distribution of galaxies produced in a high-fidelity resolution simulation shown here, then on large scales, you will see that it behaves just like the CMB. So we see some random overdensities and underdensities, just like cold spots and hot spots in the CMB, but as we start zooming in, we'll start seeing more and more complex, non-linear, non-Gaussian structure. We'll see filaments, we'll see clusters of galaxies, we'll see individual galaxies, etc. And obviously, all this structure is highly non-linear, and it will require extra efforts to understand. And the onset of nonlinearities is manifest when we try to fit some observables, such as the two-point function of the galaxy distribution. If we try to fit it with the linear cosmological perturbation theory, you will see that the fit will fail on relatively large scales, so small wave numbers. But it doesn't fail very dramatically, so it kind of fails, but in a small way. So this gives you an idea how we're going to account for nonlinearities in this regime. And the game that we're playing here is we're trying to dig out the signals of new physics that we want, such as inflation, from some background generated by galaxy formation and matter cluster in a low redshift universe. So for instance, in the context of primordial non-Gaussianity, we know that a very sensitive probe of that is the bispectrum, and we can calculate the bispectrum of galaxies and then, let's say, do a breakdown of different contributions, and we'll see that the typical contribution of new physics is going to be pretty subdominant, basically on all scales, and the observed bispectrum will be dominated by the background produced by the structure formation, galaxy formation, nonlinear collapse of matter. Our hope is basically to calculate these different contributions, one loop, tree level, one loop, two loop, and when we have very good control over these background contributions, then we can actually dig up the primordial signal. And well, you can see that the typical amplitude of the primordial signals in the context of primordial non-Gaussianity is 10 to the minus 5. of the total amplitude. So we really need some precision tools that will allow us to get to 10 to minus 5% precision. And as I'm going to argue, EFT is currently is the only tool that's on the market that is able to achieve that goal. So historically, there have been two major approaches to model galaxy formation: to use simulations that I showed you before, or to use perturbation theory. And obviously, simulations are very appealing in the sense that if we could see the clustering of pure dark matter, then simulations provide a full solution to this problem via an n-body simulation, numerical full solution. And it's valid for at any scale. The problem, though, is how to put galaxies in a simulation, how to simulate galaxies, because we don't have a first principle model for galaxies. And the best simulations that we have at the moment, they're still very time consuming. And perturbation theory is a nice alternative to that. So at some point, obviously, perturbation theory breaks down. You have some finite cutoff, so there is a limited range of applicability. But then where it applies, it actually provides you with very high precision and accuracy. And also, it's a very cheap and efficient way to explore extensions beyond the lambda CDM. So if you want to specifically search new physics, then perturbation theory is your best friend. In terms of the effective field theory of large-scale structure, I'm going to talk about. So why do we need this? Why, let's say the usual tools are not good enough? At the beginning of precision galaxy surveys, let's say 20 years ago, in principle, linear theory was totally fine, was totally sufficient to fit the data, and it's fine. You can just, use the linear equations, solve the linear cosmological equations of motion. But then the precision kept improving, and right now the linear theory is not, as I showed you before, linear theory is not sufficient anymore. And in principle, right now in this plot, for instance, the typical error bars are 5%. But as I said before, to really remove this lambda CDM background, we need a systematic tool that will allow us to get to 0.1% precision or even better. And that's why at this point, even though this is classical astrophysics, we have to use tools from effective field theory because those are the only this is the only systematic toolkit that we have. So in terms of the effective field theory of large-scale structure, there are 3 different layers, and I could not think of anything else to illustrate this as a Kinder Surprise or Kinder Egg. It's a toy and a chocolate at the same time. It's a great thing. It's also illegal in the United States. So it's the only country, by the way, where it's illegal. So I'm very happy I can advertise, I can use this analogy very legally here in Taiwan. All right, so we theoretical cosmologists, or at least myself, to effective field theory are like a kid to a Kinder Surprise. So Kinder Surprise consists of 3 things. First of all, there is a toy, which is for most of the kids the most attractive thing. And for us, this will be initial conditions. Something that probes directly the physics of inflation. Okay, so the power spectrum, the bias spectrum, skewness, other information. This is the first step in our calculations. The next step is the dark matter clustering. So dark matter clustering I would associate with the chocolate egg itself, right? It's also very attractive. Maybe for a theoretical cosmologist, it's slightly less attractive than a Kinder Surprise, than a toy itself, but it's quite good too, right? And this is something that will tell you, dark matter clustering, if we could see it, this would allow us to discriminate between different dark matter models, like WIMPs from axions and things like that. Unfortunately, though, to get to these nice things, we have to, unwrap the Kinder Surprise, right? We have to remove the cover. And the cover here is represented by galaxies, right? And galaxies is something that if you're a theoretical cosmologist, you absolutely don't care about them. But unfortunately, they represent a very significant real-world technical complication. Because what we get to see actually in the galaxy survey is galaxies, and then galaxies trace dark matter somehow, and then dark matter traces the initial conditions somehow. So we have to unwrap this whole several layers of EFT to be able to get to the nice parts. Okay, so let me walk you through these different layers. So in terms of inflation, well, I discussed already that initial conditions can be non-Gaussian or Gaussian. This is fine. We know how to include them. The next step for dark matter, we also know that in linear cosmology, that dark matter behaves like a pressureless perfect fluid, so it's simply a dust, right? But because microscopically just a bunch of quickly interacting particles. But however, in a late redshift universe, what we see is not a bunch of particles. So dark matter particles, they form bound structures. The largest bound structures are dark matter halos. And then on smaller scales, there are other bound structures. But depending on the model, this could be solitons or mini clusters or cusps or other things. So microscopically, in a low redshift universe, the dark matter distribution is very different from a bunch of particles. We see like an hierarchy of different collapse structure. And for this effective fluid created by this collapse structure, now the pressureless perfect fluid is not a good model at all. And that's why one has to use the full stress energy tensor. In general, the more general sense, we don't really know what is the distribution of dark matter on very small scales. So we have some, let's say, scale of difficulty, which is associated with the virial radius of the halo. And things are very complicated, model dependent potentially, and it will be very hard to figure things out if we are only staying within this scale. But however, as this happens often in physics, we can have some scale of difficulty, and then on a much larger scale, a simplified picture appears, right? And this is basically the EFT ideology that you were using all the time. So let's use the same idea here in the context of a clustering of dark matter. So on large scales, let's assume that we can use some coarse grain distribution. So we can introduce some coarse grain fields. And then these fields will have to satisfy basically the earlier equation. And this earlier equation will have some stress tensor. And actually we can do so, well, this effective description appears because our system in question, it enjoys a scale separation. So we have the scale of complexity, which is the virial radius of the halo, where complicated dynamics happens. And then we have also another scale of some complexity, which is the Hubble radius, where relativistic effects become important. And in between, we have a very nice range of scales where we can build this non-relativistic effective field effective fluid description, which is known as the effective field Tirov-Lashky structure. And right, as you can see in this approach, the one thing that we haven't specified yet is the structure of the stress tensor. And well, if you're an effective field theorist, then you don't make assumptions. You just use dimensional analysis and symmetries. And in this case, you can write down all possible operators that are consistent with symmetries of cosmology and Lashky structure here on the right-hand side. And so the stress tensor will start with the sound speed, and then will be higher order terms. And the rules to build these terms will be, in principle, they are set. They're slightly different from usual fluids, but very similar nonetheless. And there are some caveats. We're doing the fluid, but well, in fact, this description is slightly different from a fluid. Well, for instance, the time evolution here is very slow. It's the age of the universe. For a fluid, the collision time is very fast. So there are some technical differences, but otherwise, at the level of dark matter, we're just doing effective field theory, the usual fluid description as we normally do for usual fluids. And this effective sound speed that appears in the description is very important because it also helps, it acts as a Wilson coefficient and absorbs some UV dependence. At the beginning, people didn't appreciate this EFT ideology, and they would just start solving the pressureless perfect fluid equations from linear cosmological perturbation theory, and then they would find that loops don't improve at all. So one loop doesn't improve over linear theory result. As you can see here, this is some data. So one loop doesn't improve, and two loops, only make things worse. And this is because the UV dependence was not properly regulated in this theory. Now, however, if you include the effective stress tensor, then you can calculate one loop, two loops, etc., and then you will find a very nice match to the data. So it's very important to appreciate this, that the effective sound viscosity and other coefficients that appear in this description are Wilson coefficients that carry some UV dependence. Okay. So now in terms of galaxies, again, so this is the result of some simulation, and we can see that, the gray distribution here is the nonlinear structure of dark matter, so it is very nonlinear, as expected. And then the yellow blobs are the simulated galaxies. And the one thing that you see from here is that the simulated galaxies, they roughly they correlate with the dark matter overdensity. So wherever you see an overdensity of dark matter, also you see an overdensity of galaxies. Okay, this is like an order 1 picture that jumps at you when you look at this. But however, this correlation is not exact. So if I look at this void, for instance, this is void of galaxies. But then in terms of dark matter, I see some very rich structure. Okay, so this is something that tells you that the relationship between the two is not one-to-one. So this is another, as I said, important source of nonlinearity called the galaxy-dark matter connection. And then on top of that, there are other sources such as the baryonic feedback, redshift space distortions. So conceptually, they are very similar to galaxy-dark matter connection. So this is part of this nasty cover that we have to unwrap to get to nice parts of our Kinder surprise. So I'm not going to talk much about them, but the general idea to describe them is the same as for the galaxy-dark matter connection. So how would an effective field theorist now describe this correlation between galaxy and dark matter? Again, we would use dimensional analysis and symmetries. We would say that the overdensity of galaxies would be some function of the overdensity of dark matter. And then the simplest function you can think of would be a linear function. And then we can go on and write down more complicated operators in our Taylor expansion, delta square. At some point, we can write down the tidal tensor because it's allowed by symmetry, so we must include it. Okay, then there are some other terms that we cannot write down, so we cannot use the velocity field because it will break the Galilean invariance. We cannot use the gravitational potential. This will break the equivalence principle. So in principle, again, we have a very clear program how to write down all these operators and describe the galaxy-dark matter connection. And by the way, the fact that the galaxies are correlated with dark matter on larger scales just simply follows that the linear function is the simplest relationship that you can write down. And it's important here again to appreciate that in this description we have a bunch of nuisance parameters, B1, B2, BG2 that capture the galaxy, the galaxy-dark matter connection. And again, these are some Wilson coefficients that we have to match to the data to be able to extract cosmology. All right. So let me give you a little taste of calculation when the EFT of large scale structure in the context of this galaxy-dark matter connection. So let me truncate this expansion of the quadratic order and assume that the dark matter field is a Gaussian random field. So its initial condition just, it has only Gaussian correlation. So its two-point function is given by the power spectrum, which in linear theory is given by this function that you can extract from your favorite Boltzmann code. And this linear power spectrum will play a role of the propagator in our calculation. So now, if I want to compute the two-point correlation function of the galaxies, I just have to square this expression and take a statistical average over it. And the leading order term will give me a linear contribution. Then there will be a term with 3 insertions of the matter density. And for Gaussian initial conditions, this term will be 0. Now, if the initial conditions are not Gaussian, it will not be 0. And from this example, you can see how primordial non-Gaussianity affects the effective field theory of large scale structure calculations. And then finally, there will be a term that comes from squaring of delta square itself. So the product of two fields in position space and Fourier space, it will be a convolution integral given by this formula. And in this simple example, you see how loops appear in large scale structure just from the fact that we're doing nonlinear perturbation theory and ensemble average. Right? There are no quantum effects, nothing. It's purely classical calculation. And other loops that appear in the context of EFT, they have at one loop order they have the same structure. Typically, well, at one loop order there are two linear power spectra, and then possibly there could be some kernel that depends on the external momenta and the loop momenta, but the general structure will be the same. And you can write down a Feynman diagram associated with this loop integral, and then we can carry on and include more higher order terms and write down more diagrams. And in principle, again, we have a very well specified set of rules how to build this perturbative expansion in terms of the Feynman diagrams. Okay, now one important point is about the evaluation of these loop diagrams. So in general, this is quite hard because this linear power spectrum is only known numerically, right? It's not a nice propagator that is 1 over k squared. It's some complicated function that doesn't have an analytic expression. The way to evaluate this, however, is to approximate it as a sum of different power laws, and the most successful way is to say that it's a power loss. Oops, try it again. Okay, it's a power loss with the complex exponents that basically is just a Fourier transform in a log k space, and hence the name FFT log. So if you use this ansatz, if you plug it back in your loop integrals, then you will end up with the three-dimensional loop integral with the this integrand that has two generic anomalous dimensions. And this integral can be easily solved, and probably in this audience, everyone already knows the answer from the Smirnov book. So this is the answer. And this was historically one of the first ways how we sort of understood that using the connections with amplitude and with loop integrals from other fields can be beneficial, extremely beneficial to cosmology, because using this formula allowed us to basically slice the computation time from hours to seconds. And let me also say that this technology works very nicely at one loop, but beyond the one loop power spectrum, like other integral representations that we have for other things are not very efficient. So this is a great place maybe for some of the experts in the room to contribute to extend this sort of calculations to higher order statistics and higher order loop corrections. Okay, so another really important effect is called the infrared resummation. So some of the loop corrections that appear in this expansion, both for dark matter and for galaxy bias, so they look like this. At one loop order, it will be proportion to the linear power spectrum, and then there will be some loop integral that has a pole in it, 1 over q squared, where q is loop momentum. And this integrand multiplies the difference between these two propagators. And if the power spectrum were a power law function without any features, then you could Taylor expand this, and this would undo the pole. But however, the power spectrum in our universe does have features. Well, at least it has one feature, which is the baryon acoustic oscillations. And in this case, you cannot Taylor expand this thing, and you end up with a diagram that is enhanced in the infrared. And this is something that produces very undesired effect on the observables. So if we go now to position space, so Fourier transform this, then this feature, the baryon acoustic oscillation feature, will look like a Gaussian peak, roughly at 100 megaparsec over h. And it's been known for many decades that the prediction of the linear theory is much more enhanced than the actual results in the embodied simulation. And if you try to account for this at one loop, just using this formula, then you're going to see this red curve that sort of doesn't make things much better. And this exemplifies this IRS summation story. So the way to go around is to actually resum the perturbative expansion and resum all contributions that have the poles. And it's really a very beautiful problem in this approach, and there are different techniques that you could use, and in the end they all give you the same answer. And there's also very significant input here from the symmetries, because you are able to resum these contributions because their structure is controlled by the equivalence principle. Well, altogether, if you carry out this resummation, then you're able to, in the IR resummed version of the one loop power spectrum, you're able to very nicely describe the suppression of the baryon acoustic oscillations. And then when you put all these things together, it works. So now, there are several public codes that compute these nonlinear corrections, both for dark matter and galaxies and other observables, including IR summation. And now, finally, we can nicely describe the data. For instance, the code that I produce, you can find on my GitHub, and I have a lot of notebooks and other things that you can play with. And also recently there appeared more codes on the market, so it's a very competitive field now. And okay, so once we have all these calculations done, we apply them. Oops. Okay. Once we had all these calculations done, we started thinking of applying them to data, but before that, we wanted to make sure that all the stuff that we're doing makes sense. So we're sure that effective field theory is correct. And of course, as I said, it's based on this very solid physical ideology of the EFT, but also we have done many explicit checks, such as we participated in the blind challenges, such as the PT challenge organized by Takahiro Nishimichi, where we were able to extract the unknown cosmological parameters from the data whose volume is 100 times bigger than the volume of the, well, our universe in a sense. And the typical error bars were 0.1%, so 1% was that big. So this was a very big success for us, after which we realized that, oh, this EFT probably indeed sort of makes sense. And after that, we also participate in many other challenges, most recently the Beyond Two-Point Function Challenge organized by Elizabeth Krause. Another interesting test that you can do is to apply the effective field theory of large-scale structure at the field level. Because we have we have these different operators that control, and we have a lot of Wilson coefficients that control the amplitudes in front of these operators, but we have 0 fitting parameters that control the phases, right? And so this is something that EFT gives a unique prediction for. And now we can take the initial distribution of dark matter from an n-body simulation and forward evolve with using EFT instead of the full n-body. And then we're going to get a result that is basically indistinguishable from the full simulation. And again, let me say this Millennium simulation is, well, possibly the best simulation that the humankind ever produced. It took a lot of CPU hours, and this image on the right is something that I generated on my laptop in 1 minute. And you can see that on large scales, these two distributions are basically indistinguishable. So of course, the EFT field is more fuzzy because EFT breaks down small scales, but otherwise, all large-scale features are captured very well. So it means that EFT works for any correlation function. And again, the success of the EFT is not due to the extra fitting parameters, but because it does capture physics correctly. And after having done all these checks, we applied this technique to the reanalysis of the publicly available data of BOSS, and were able to measure cosmological parameters with precision that was very similar to Planck. That was very surprising for us. And I guess this was the first, the first big success of the EFT of large-scale structure. And after that, well, there was some back and forth, but now it has become the standard tool that is adopted by major collaborations. And a couple of weeks ago, I was really excited about the DAISY results, and they use the EFT-based full-shape analysis as their main analysis choice in their papers. So this tells you that now it's almost universally recognized that the EFT is the right way to describe large-scale structure. Okay, now let me say that, yeah, we produced all these results for the standard model. We're able to measure the usual cosmological parameters with the one-loop IRA summed galaxy power spectrum, but we really have in mind testing this, exotic beyond standard model extensions. And I said before, the most interesting for us are dark matter and inflation. We also did a lot of work that addresses the Hubble tension in the context of dark and exotic energy injections. Okay, this is something that I don't really have time to discuss, but if you have questions, let's chat offline. Let me give you some examples of the application of the EFT technique to dark matter and inflation. So in the context of dark matter, I guess the worst case scenario for any particle physicist is that dark matter doesn't couple to usual particles at all. It only has gravitational interactions. And probing this will be very hard. But however, it is possible to do so with galaxy surveys if you assume that dark matter has several components. So both of these components can be perfectly decoupled from the standard model sector. But if one component is not exactly cold, this is a regime that we can test very, very precisely with galaxy surveys. So if that is the case, if we have, let's say, at least two components, one of them is perfectly cold dark matter, the other one is not exactly cold, then there will be some effective gene scale beyond which the second component doesn't cluster. And in this kind of scenario, again, CMB is not very sensitive to it because of a very nice statement called the Weinberg decoupling theorem. So it's another decoupling theorem about the decoupling of dark matter from the CMB. And in this case, basically, galaxies, provide a very nice way to test this scenario. And the presence of this effective gene scale will lead to the suppression of the galaxy power spectrum. And roughly the amplitude of the suppression will tell you the abundance of this extra component, and the scale of the suppression will tell you the mass of this component if you assume that dark matter is some sort of particle of the mass. An example of this is our recent constraints on the string axiverse. So scenario where we have several axions, let's say 2 or 3, and one of them would be cold dark matter, the other one would be some light component. And here you can see that the results we obtained with both EFT pipeline and Planck. And you can see Planck CMB, and you can see that for some, this way is much easier to do it on the screen. Well, you see that for some axion masses, our constraints from Bose alone are stronger than the constraints from Planck. And in general, if you combine the two probes, then we can get constraints on the abundance of the axions, depending on the mass, that could be as strong as basically sub %. So this is one example where we can test the string axiverse scenario with galaxy surveys. And then we also worked out many other examples. For instance, you can test the interaction of dark matter and baryons. You can test all possible modifications of the dark sector, dark matter interacting with dark radiation, neutrinos interacting with dark radiation, etc. So many of the scenarios, in the same ballpark, same rubric of non-standard dark matter. So all of these things now we can test with galaxy surveys very precisely, thanks to the EFT. So another example is the application to inflation that we discussed before. So now we have a very precise model for this background. We can subtract the background and really test your favorite inflationary model. Well, we started with the kind of standard analysis of the equilateral and orthogonal templates that follow from the effective field theory of inflation. So if you assume that there is a single degree of freedom during inflation, and you can work out its EFT, at least in order it will be 2 parameters in your effective Lagrangian, and we constrain these parameters. You can see our constraints here on the right. And in this sense, what we're doing here is very similar to the precision electroweak tests, but at the level of cosmological large-scale structure. And most recently, we extended this to the cosmological collider scenario. So that was discussed, I believe, at this workshop before. So that is the decay of a massive particle during inflation. So, and if that happens, there will be a specific shape of non-Gaussianity that actually is not captured by any of the standard templates. And this analysis in the context of CMB is very hard to do because CMB is based on these factorizable templates, and here in large-scale structure, we don't have to worry about this. We can just calculate everything without worrying about factorization. So that's why this analysis was possible in full generality. And with my collaborator, Giovanni and Oliver, we were able to get some reasonable constraints on the mass of the massive scalar coupled to the inflaton during inflation. So the constraint on the effective mass was greater than 1. That I guess is expected, but still, nevertheless, it's a very sensible constraint. And this could be the the first constraint on a particle whose dynamics happens at 10 to the 14 GeV. Hopefully, in future with megamapper now, we'll try to sort of push for the cosmological collider scenario to become a standard kind of driver for future surveys. All right. So now, in terms of improving the EFT in future, one important application will be to actually build some interface between EFT and simulations. So if you ask this question, what kind of constraints on inflation we can get with this technique with future surveys, even with megamapper, then you will find that your result depends a lot on what you assume about this Wilson coefficients. So if you don't know anything about them, so if you want to fit both the Wilson coefficients and non-Gaussianity, then the best you can get is FNL, let's say, equilateral of order 10. You cannot really push beyond that. And there is actually a very nice target, which is FNL equilateral 1, that was explained to me that, well, basically will tell you if the UV completion of inflation will happen the UV complete model will be strongly coupled or weakly coupled, so it's very attractive theoretically. But in order to get there, we have to use better price on nuisance parameters. So if we assume that we know the galaxy formation Wilson coefficients exactly, then we can see, you can take a look at these curves below, and you can see that the constraints, for instance, on the FNL equilateral can be much better than 1, okay? So if you want to really probe this theoretically motivated regime, then we have to understand galaxy formation, and we have to use simulations. So, and this was a big motivation for me to really get into this and to get priors on EFT parameters from simulations. And this is something that we've been doing with my group at MIT this year. And basically, conceptually, it's very similar to matching chiral perturbation theory parameters from different lattice QCD models. Let me show you some results of this work. So we were able to generate large set of cosmological galaxy simulations, and then we measured their EFT parameters. And these EFT parameters happen to be very correlated, as they should be for any exact, let's say, UV model, right? Like a complete UV model. And these correlations in general are very non-Gaussian, and then we use the neural density estimation based on normalizing flows that allows you to capture this non-Gaussianity very precisely. And then this way we're able to model this distribution and apply this as a priors in the EFT full shape analysis. And this allowed us to improve the constraints from BOSS by 40%. And this is basically as good as you can get from BOSS. And this is the same improvement as you would get by just fixing the bias parameters as we did in the forecast before. So this exercise basically showed me, well, convinced me that if you combine EFT in the simulations, then we can get to FNL less than 1. And yeah, I believe that this is the way really to probe inflation. And that's why the last year I've been really working a lot on this galaxy formation. I guess another realization that happened relatively recently is that this effective field theory Flaschke structure technique is very general, and it can be applied to many tracers in cosmology, to Lyman alpha forest, weak gravitational lensing, galaxy shapes, bispectrum parity violation. There are some non-perturbative contributions in terms of the counting cell statistics that you can calculate using the semi-classical instanton calculations, etc. So basically, we see that in large-scale structure in our universe, most of the data is actually in the perturbative regime, or at least a very significant fraction of it. And this is something that is totally new, and this opens up many exciting research directions. So recently, I've been also very excited about applying EFT to Lyman alpha forest with my group, and here you can see some results from the reanalysis of the public data on the Lyman alpha forest, where we're able to get some really nice constraints on the neutrino mass and the dark matter clustering in the low redshift universe. Let me end my talk with a few open questions in the field, because it seems like this field is very mature. Oops. And lots of things have been done, but in fact, there are many open areas and many open questions, and something that you people in this room would certainly, you could contribute very significantly. So obviously, it will be very nice to push this calculation to higher orders. For instance, the current frontier would be a two-loop power spectrum and bispectrum for galaxies. Also, the trispectrum is totally uncharted. So even the trilevel trispectrum, so 4-point function, has not been computed. And then, once we compute these things, it would be nice to think about a fast evaluation of this loop integrals. And in particular, for the two-loop integrants, there is a formula from the Smirnov textbook that looks like this, where k would be some function that is represented as a series. The problem with this formula is that it converges very, very slow. So this formula doesn't really work nicely. And that's why, if you have ideas how to compute this integral, then please come and chat with me. Another input that I would really appreciate is new ideas and models in terms of the cosmological collider. So as I said, we're trying to push the cosmological collider program more and try to motivate future surveys using these scenarios. And that's why, if you have a model that has some nice physics in terms of inflation cosmological collider, I would really love to learn about this. And as I said before, EFT really has a lot of potential when applied to testing non-standard dark matter scenarios. But for many of the scenarios, actually some extra calculations will be needed. So we'll have to introduce new loops, we'll have to introduce new counter terms, new fields, etc. So for instance, for axion light relics, there will be some new components, something that we have not included yet. And this is another way, it's another field where you could contribute. Yeah, and then there is a very technical point, IR summation ratio space for endpoint functions. If you like symmetries and resumming diagrams, okay, this is a place for you. All right. Let me summarize my talk. I hope I have convinced you that effective field theory flash key structure is a robust analytic tool for various kinds of tracers in a late redshift universe. And also I hope that I've convinced you that our universe is the largest collider, and we can probe things that otherwise are impossible to probe, such as particles at energies of 10 to the 14 GeV. And also large EFT flash key structure gives us novel ways to test new physics, such as to use the shape of the galaxy power spectrum to test different dark matter models. And with these tools, we expect many improvements in future when we apply these tools to data from surveys such as Euclid and DAISY and MegaMapper. And hopefully, as a result of this application, many questions on inflation, dark matter, and dark energy will be answered. So I think I'll stop here. Thank you.
Thank you very much. Okay, yeah, thanks for a nice talk. Can you maybe elaborate the part where you extract the bias parameters from the simulations? Because I was a bit confused that whether these simulations are for dark matter or for galaxies, and how do you use them to extract?
Yeah, that's really a great question. Thanks. So the way we extract them actually is that we precisely do this. We extract them at the field level. So what we do is we produce a bunch of simulations that look like this. That really we have a full density field, and then we match this with an effective. We just feed this field with the effective field theory model. And this is something that just gives us the cosmological parameters, the bias parameters right away. And the advantage of this approach is that when you match things at the field level, you don't pay the price of cosmic variance, right? Because you evaluate these things for a given dark matter realization. And that's why you can cancel cosmic variance. So you can get very precise measurements of bias parameters, even from very small box simulations. Right, so for instance, Millennium is only 500 megaparsec, and it's considered to be the biggest cosmological simulation. Now with this, but it has a cosmic variance because, like, I don't know, the volume of BOSS, for instance, 6 gigaparsec, right? It's like 10 times bigger than this. Okay, using EFT and high fidelity simulations on small scales, we can carry out this program very, very efficiently, and we don't need to run these expensive large volume simulations.
More questions? You?
Hello. Okay, so your effective field theory results the power spectrum is extend only to like 10 to the -1, which is just starting the nonlinear cell starting deviate from a linear power spectrum, so, and that's for the two loop, and there's a deviation from the simulations, right? So, what do you expect in the futures? If you want to extend to very low, very small scales, how many times? Like how long the calculations takes or compare with the simulations?
Yeah, thanks. Yeah, this is a really great question. So I guess you're referring to this figure, right? So here we're already hitting nonlinear. Nonlinear here is like the cutoff of the EFT here is 0.5 H over megaparsec. And we're already with 2 loops at 0.3, right? So probably it doesn't make sense to compute 10 loops, right? Because we're already very close to the cutoff. So unfortunately here we don't have any systematic tool to compute. Like, EFT breaks down at the cutoff, we cannot do anything about this. On small scales, you can use the simulations, you can use phenomenological models, but there is no systematic way to use this information. So I would say that actually the bulk of information actually sits on large scales in any case, right? Because there is no reliable way to extract the small scale information.
Thank you.
Yeah, so I have a question about, again, that plot that was showing the comparison between the EFT result and the simulation. I was,
Which one?
yeah, the one of the previous question. No, the one in which you had the EFT result discussing how well you can.
The field, oh yeah.
So
yeah.
I was wondering which are the inputs that you use to get the result on the right, in the sense, how much did you use of the Millennium simulation? Nothing?
So right now, okay, to reproduce this image, what we use is we use the initial conditions, the initial realization of the dark matter field, just the initial Gaussian field, right, that we evolve forward. And well, to produce this result, we actually use the final catalog of Millennium, measure the bias parameters, because to reproduce this clustering, we still need to measure them, and we kind of match the bias parameters from the snapshot on the left, right? So we kind of try to optimize the bias parameters by fitting the field on the left with the EFT model, but then this EFT model only has very few parameters to begin with, right? So it's, I mean, again, from theory, it should be like this, just based on symmetries, but naively, it's unclear that with only 5 parameters, you'll be able to capture this entire snapshot.
I see. But you still need the Millennium simulation
Yeah,
in order to produce the.
Yeah, absolutely. Yeah, absolutely true. Now, what we could do, yeah, because here the idea was to really reproduce it, right? The best that we can with the EFT. So this is like the EFT of the parameters that match the Millennium galaxies. Now, you can forget about the Millennium and just take the initial snapshot and use some bias parameters that you want, and you will get a very similar snapshot that simulates some other galaxies, right? And this is something that you can produce in a split second, right? So in principle, this is how you can use EFT to well, for many other problems. For instance, sometimes you can have a simulation that is too small, only produces small scales. That is always the case for hydrodynamical simulations. And then if you want to get a bigger map, what you can do, you can, let's say, measure these bias parameters from a tiny box and then produce a gigantic, the entire universe, okay? Just using the bias parameters that you want, that you measured from somewhere. And then this big, like synthetic simulation done with the EFT will be on large scales as good as the full simulation. So there are different ways how you can.
Yeah. Sorry, can I maybe follow up on this slide? So what's kind of the size of the systematic error in the Millennium simulation? Because so your statement about FNL equilateral 1 sounded very encouraging, but presumably you need to then trust simulations, including variance, at kind of this 0.1% level accuracy. So what's the spread if I run different simulations with all these knobs that baryonic simulations have? What do you need to do to trust things at the level that you need?
Yeah, that's really a great question because, good. Okay, the situation right now is not very promising. What we have done, we started the Millennium simulation, and then we took another simulation, Astrid, that is run with slightly different assumptions. Then we selected the exact same galaxies, and we found bias parameters that are order 1 different. So I think that we'll have to understand better how to combine different hydrodynamical approaches.
More questions, Misha? If not, then let's thank him again for a very nice talk.